Welcome back to the sixth lecture on this course on computational fluid dynamics. In this second part of lecture 6, we're going to explore why the solution to the transport equation we saw at the end of the last lecture section was unstable at high Peclet number. What we're going to see is that the concept of information flow makes an appearance again. If you recall, when we examined the solution to transit problems last lecture, we recognised that we didn't know what the future was, so the discretisation schemes for time that involved the future made no physical sense at all. In transport equations that are strongly dominated by convection, we're going to see a similar, albeit slightly more subtle, embodiment of this concept. When flow velocities are high enough, the direction of movement of whatever the subject of the transport equation is physically dominates the problem. It outweighs all the other terms, and so consequently, when we consider how to discretise gradients that involve convection, we need to take that physical situation into account. Now, we're going to find a way of making the solution to this problem stable, but in doing so, we're going to introduce another error, an error of great subtlety. And it's not until the predictions of the transport equation are analysed in a subtly different way that we actually see what that error is. Once we've identified that error, we're then going to suggest ways in which we can solve it. Now, let's do a little bit of a recap about information flow. We saw in the last part of this lecture unphysical oscillations in the solution to this transport problem where the Peclet number was high, where convection dominated the problem. If we think back to last lecture and our initial value problems, and we started to solve our time-dependent problems by using central differencing for time, and we realised that we can't do that because the future hasn't happened and it makes no physical sense. If we think of our spatial discretisation for that convection term. Our convection term, if you recall, was Vx dt by dx. And we said for dt by dx, let's use second order accurate central differencing. And here on the board, I've put our three nodes, I minus 1 and I plus 1, and our central difference terms, ti plus 1 minus ti minus 1 over 2 delta x. Now, let's just think physically. It's very easy when you're dealing with inherently mathematical problems to forget about the physical situation that you're dealing with. But it's really important that you do remember the physical situation and think about it. Now, let's imagine somehow that we can stand at node I. There we are, standing at node I in our fluid flow, and what we're doing is we're feeling temperature. Now, when the fluid is stationary, if we have heat transport by diffusion only, then where I am at node I can feel temperature flow from either of my nearest neighbours. It can come from the downstream end, from Ti plus 1, or it can come from the upstream end at Ti minus 1. There's no fluid flow in this stationary state, so it doesn't really matter. So this is analogous to solid heat conduction. Now let's imagine we have a flow. The flow direction is coming from node 1. And so if I think of my two nearest neighbours, it's node I minus 1 that I feel that fluid flow coming from. And so if my fluid flow is very, 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 very slow, I can still get temperature information from Ti plus 1 so long as the rate of diffusion is quick enough. If the rate of diffusion can outpace the rate of convection, then I will still feel temperature at node I coming from that downstream direction. However, as we sequentially increase and increase and increase our fluid flow velocity, convection is going to outweigh diffusion. The molecular transport mechanism simply can't go fast enough to have any influence over my temperature at node I. And so any temperature information from node I plus 1 does not make physical sense. Because once there is enough convection, the only temperature information I receive standing at node I comes from the direction of the fluid flow. If we imagine the fluid flow as a wind, if we face up into the wind, we will feel all the temperature coming towards me. So this is where the origin of the term upwind discretisation comes from, and this hopefully highlights the really important point of always keeping tabs on the physical situation for which you are solving the mathematics for. So we cannot use centred differencing to discretize the spatial domain for convection terms. It doesn't make any physical sense, because due to convection, the only gradient that makes sense is going to be involving the nodes upwind of me. So I need to reflect that in the transport equation that I produce. So I'm going to change my mindset. I'm going to think for convection, the important thing that determines the convection-based temperature gradient is going to be the information flowing towards me in that flow. And so I will approximate dt by dx as ti minus ti minus 1 over delta x, because node I plus 1 has no influence on the convection at all. And so we're going to call that ti minus 1 over delta x, my simple first order backward difference, an upwind difference. Remember that analogy of facing into the wind and looking at the information flow coming towards you. So here on the board I've put the altered transport equation. The only term I have altered is the convection term, and this is a really important point. We only use upwind differencing in those terms that involve convection in the first place. I haven't changed my conduction terms, that's still using centre differencing, because the physical mechanism of conduction can be influenced in either direction. The physical mechanism of convection can't. It is only influenced in one direction. And of course none of this actually affects how my heat source works. So there's my change transport equation. Here is a reminder of the flow situation that we've got, and here is the solution that we saw before for weak convection. Now let's run the solution again with that change discretization, that upwind discretization for my convection terms, and we see that our previously unstable solution is now stable, and so that looks really good. We can nitpick about whether they should asymptote to the same value, but since I've only said weak convection and strong convection, not actually put velocity terms on here, then the exact point at which you get that steady state temperature is hard to judge. So this looks like problem solved, doesn't it? But, as you might have guessed, it's not. Because we used first order upwind differencing. We used a discretization scheme that we actually recommended not to use at all, if you recall. It's only first order accurate. But if we just looked at those temperature profiles, we wouldn't see the effect. Now, we need to analyse the results of this model in a slightly different way to actually see the effect of using that first order term. Just because the solution is stable doesn't mean it can be correct. It can still be wrong, it can just be wrong in slightly less obvious ways that are easy to miss. So, I want to illustrate this in a slightly different way. I want to change my attention to mass transport because it makes the mental model and the thought experiment easy to visualise. So, we're going to think about one-dimensional convective mass transport, the exact analogue in the mass transport world to the thermal problem that we've been analysing. So, the partial differential equation that we have is the change of concentration of species with time is going to be equal to diffusion terms, there's my second order derivatives, the diffusion terms, less convection terms. And don't forget that minus sign is there because of the v dot grad c term that would have appeared originally in the total derivative along in the left hand side along with that partial concentration derivative. To simplify things even further, I'm going to say two things. Let's forget about reactions, and so you'll note here that there are no source terms. And we're going to say even more simply, let's turn off diffusion. Let's just simplify this to the simplest possible thing that I need to illustrate the point I want to make. And so what we have now is zero molecular diffusion, and in effect the equation that we have is the 1D wave equation. And we look at that and we know there's an analytical solution to it, but we're not going to cover that here. So we're going to discretize this. We're going to have spatial discretization based on upwind differencing on the right hand side, first order method, and then we'll integrate using a fourth order Runge-Kutta method. You'll note that the matrix will be simpler here, since we only have Ci and Ci minus 1, so we only have a diagonal and a subdiagonal to solve for. So it's a bidiagonal matrix, not a tridiagonal matrix. So that's the maths of it. Let's get to the nub of the physical scenario so we can perform this thought experiment. Now, here on the board, I've put a diagram of a one-dimensional flow domain. There it is, it's an infinitely wide slot, and I'm saying that it's got a plug flow velocity profile. So Vx is constant. The only gradients, again, in common with the thermal problem, are going to be in the x direction. What I'm going to do in my mental model is I'm going to get a syringe of tracer, a nice coloured liquid, and in the colourless liquid, say water, that flows through this slot, I'm going to inject a square pulse of coloured dye at the start. And then I'm going to look at how that coloured liquid transports in the problem. Now, remember, we have turned off diffusion. And so the only way in which that square pulse can move is by convection alone. The boundaries of that square pulse, if we assume they are sharp to start with, can't be blurred. The pulse can't spread. With diffusion, of course the pulse could spread. But remember, in the numerical world, we have the luxury of being able to turn on or turn off different physical mechanisms at will. Since I've turned off diffusion, there is no physical mechanism for the dye in this tracer to spread. So we inject a square pulse in, we expect a square pulse out, because everything will have been moved with that same plug flow velocity equally. Okay, hopefully you're happy with that mental model. What we'll do now is to look at the predictions that the numerics state. So here on the whiteboard I've got a small movie of how that pulse of tracer convects through my fluid flow domain. Can you see the problem? It starts off a square pulse, but then look subsequently what happens. If we hadn't explicitly stated that we had turned diffusion off, we might be okay with what we're seeing. But we have turned diffusion off. What you are seeing looks like a diffusion mechanism, doesn't it? And since there is no physical mechanism for diffusion within the transport equation, this has to be an error that is numerical in origin. So here on the board is a summary of what we saw. We had a square inlet pulse, and that we saw as that pulse moved through our solution domain, it became more Gaussian shaped, which it shouldn't do, because we don't have molecular diffusion as one of the transport mechanisms in this problem. So what's going on? Well, it's thanks to first order upwind differencing. It's a first order accurate method, and that means we're getting numerical diffusion. So it's a numerical scheme that's actually causing this physical looking mechanism. What we also find is that the situation gets worse, because if we integrate under each of these different pulses, which is in effect undertaking a mass balance, we see that the mass in does not equal the mass out. So somehow, not only are we getting this numerical diffusion, but we're also getting something called dispersion. We're getting a loss of mass. And so first order upwind differencing is the key thing that is responsible for both of these mechanisms. Now perhaps you can see why in the transport equation I turned off diffusion, eliminated those terms to illustrate this point. With diffusion terms turned on, we might have convinced ourselves that this would be the expected outcome. But with a lack of diffusion, we can see that that is not the expected outcome. So we need to do better than upwind differencing, and we need to be able to bypass these problems. So what we need are higher order methods, and I'd like to introduce two higher order methods to you, one of which that you will see implemented within Fluent. Now, the first scheme is called SPUDS. You'll find that numericists love their acronyms, and SPUDS is an acronym for the single point upwind difference scheme. It's I've written in terms of space derivatives here, so dc by dx is going to be what looks like a central difference to start with, but then with upwind-biased differences to correct it, to keep the information flow correct. And what we find is that this will be stable, third order accurate, and conservative, and so we don't get mass loss or mass gain. A very close cousin to SPUDS is something called QUIC, and you'll see QUIC implemented within the Fluent code, and this stands for Quadratic Upstream Interpolation for Convective Kinetics. The only difference between SPUDS and QUIC is a factor 8 in the denominator for QUIC versus 6 in the denominator for SPUDS for those second terms. QUIC will also be stable for the problem that we're solving, it's also third order accurate, and it is also conservative. So what we're going to do now is use both SPUDS and QUIC in the solution to our dye tracer experiment and see what they predict. Now, before we do that, a quick note on how using these higher order schemes changes our matrices, which changes computational resource. So we're still solving this transport equation. We were still solving a ordinary differential equation, I've written it in terms of temperature here, equal to an algebraic linear system. Now let's think about matrix M, because if we think about simple upwinding, we've got a tridiagonal matrix if we've got diffusion included. And if we use an upwind difference scheme, we'll see that we've got an extra node involved in the evaluation of the gradient. Okay, it might not look that much, but if we think about what this means from a computational standpoint for a large problem, if we're doing convection and diffusion together, then SPUDS and QUIC will require a third extra memory per spatial dimension to store matrix M. And if we've got a nice banded matrix such as this, then all the matrix will be stored in memory for that direct inversion. For the indirect methods, you will still need to store an approximation to that matrix in memory, which means that you'll still need more memory in which to store it per spatial dimension for these higher order discretization schemes. If we were just solving a convection problem alone, if we turned off diffusion, then actually we've got 100% more memory that compared to simple upwinding when we look at SPUDS and QUIC. So one of the things to remember is that higher order schemes will always involve more memory, and depending on the scale of the problem that you're solving, this may or may not be a problem when compared to the compute resource that you are using. So here on the board are the predictions of the code for this problem. One uses SPUDS, one uses QUIC. Now both of these little movies are playing simultaneously. You can see the square wave being started at the front end, and you can see the way that square wave moves along the solution domain in both senses. Now it doesn't seem too bad. It's definitely an improvement on first order upwind differencing, but you will see that the solution isn't that perfect, and it's not perfect because I've asked in effect this code to do something that's very, very hard. I've given it quite a coarse solution domain, so the nodes are spaced quite wide apart, and also I've turned off diffusion, so it's an infinite Peclet number. And so in a sense it's the hardest problem for both SPUDS and QUIC to solve, which is why it's struggling a little bit, and you can see a little bit of oscillation at the leading and trailing edges of that square wave as the solution progresses. So here on the board is a summary of the two performances there. We can see that SPUDS has a little bit of oscillation at the top of the pulse, and QUIC has a little bit of oscillation on leading and trailing edges. If our grid was finer, then we wouldn't have seen those problems. I wanted to demonstrate that SPUDS and QUIC aren't a perfect solution for every case, and purposely made the grid pretty coarse, and also purposely turned off diffusion, which would have actually stabilised this problem. We call this error Gibbs error, and for those of you of an electrical engineering bent, you'll realise that this looks a little bit like pulse ringing when you're switching, and in the absence of a Schmidt trigger or something of that nature, you would have a noisy pulse which can cause havoc in switching systems. So what we find is that we can solve the upwind problem using multi-point schemes. Now, pros and cons of upwind schemes need to be thought about. They're more accurate than simple upwinding. They're less prone to dispersion, only mildly prone to dissipation, and manipulation of delta x, your grid resolution, will make these in effect fit for purpose usually. Now, they can be prone to this little bit of oscillation. Again, this can be solved by our grid resolution. They're linear and they're easy to program. These solutions are programmed up in MATLAB for a point of reference, but the thing to remember is that when you're using multi-point schemes, they do need more storage space in memory, And so depending on the scale of the problem you're solving, you might want to look quite critically how much RAM you've actually got on the computer that you're using. When we think about the structure of that sparse matrix, we only need to construct it once. If we think about the terms within that matrix, they just involved our grid size, and so long as our grid size doesn't adapt, that matrix can stay constant. So you construct your matrix, which can be time consuming for large matrices, and then just use it. So that's a pro. We'll see other methods where the matrix M needs to be constructed at every iteration, which is time consuming. There are higher order extensions of both quick and SPUDS. We can go to fourth or fifth order accurate if needed. Now, for most convection diffusion problems, when you actually do have diffusion turned on and you don't have an infinite Peclet number, you'll find that these multi-point schemes are absolutely fine, and they'll probably be the ones that you default to. However, there are some physical things in nature that actually are very sharp-edged. If we think of a bubble moving through a flow domain, the bubble interface doesn't diffuse. That is where it is. So that's a very good example of a very sharp discontinuity between one phase and another. If you think about aerodynamics and think about shocks, a shock is a very, very sudden change in physical properties of our fluid and of course, the fluid velocity. That doesn't blur or diffuse. And so sometimes, not even multi-point schemes can be suitably accurate to capture very, very, very sharp changes of gradient. So we're going to see what we do in these situations in the next part of this lecture. Let's recap a few key points. The key point of all that I wanted to put across in this part of this lecture was that information flow is crucial to understand when you're discretizing convection diffusion problems. When we think about using upwind differences to take into account information flow, we need to only apply them to the convection term within the transport equation. Just a convection term. Don't cover all the terms in that transport equation with upwind-biased differencing. It's only the convection term that needs it. We saw that first order differences are very inaccurate, but they're stable, and that can give us a false sense of security unless we look very closely at the solution to the problem we get. If we think about that 6-step validation, when we think about validating a mass balance, that's where we would have seen the error. When we plotted out the time-dependent transport of that mass pulse, we saw the pulse broadening out. That is a very powerful way of observing what the error is. So higher order upwind-biased methods such as quick and SPUDS can be used with reasonable accuracy for convection diffusion problems, but at the cost of extra memory.